Imagine you are, just cruising down the highway in your electric vehicle. The radio is playing, the ride is super smooth, and you've got a really solid state of charge according to the dash.
Right. Everything is just totally normal.
Exactly. You're doing maybe 70 miles an hour, keeping pace with traffic, and then, out of nowhere, no warning at all, the dashboard just lights up like a Christmas tree.
A very terrifying Christmas tree.
Oh, absolutely. A severe, bright red warning message flashes right across the main screen. And suddenly you feel the car physically react, like right beneath you. The pure electric drive torque just drops out entirely.
It just cuts the power.
Yeah, your speed is drastically slashed. You press the accelerator, but the car feels like it's, wading through deep mud. It basically forces itself into this heavily restricted, low-power hybrid mode.
Just bleeding off speed so you can, limp over to the shoulder.
Right. And your heart is pounding. You're sitting there on the side of the highway wondering, what on earth just happened to my car? Like, what is going on deep inside the physical chemistry and the computer brains of this machine to trigger such an extreme, violent reaction?
It is an incredibly jarring experience for any driver, without a doubt. But from an engineering perspective, what you're experiencing in that split second isn't, it's not a glitch in the matrix. It's not some random software bug.
It's intentional, right?
Totally intentional. It is a highly orchestrated, incredibly complex fortress of safety protocols, basically slamming its blast doors shut to protect you. The car is literally crippling itself on purpose.
And understanding that invisible fortress is exactly our mission for today's deep dive. We are unpacking a highly technical, really dense engineering document.
Yeah.
And it focuses on what the authors call the fourth dimension.
Yeah, the software algorithm and control logic layer.
Right. Because when we talk about batteries, we usually just think about chemistry, right? Lithium, physical metals, liquids. But today, we are looking at the software that actually governs that chemistry.
The brains of the operation.
Exactly. Specifically, we're going to decode what is basically the ultimate doomsday code for a high-voltage battery system. And that code is BMS067.
Yeah, A067. To put the severity of that specific code into perspective, in advanced vehicle control systems, the proprietary architectures and industry-leading EVs, that code is the ultimate red alert.
The big one.
The biggest. It's the code that signifies the battery's physical capacity has degraded down to its absolute irreversible limit.
So the battery's just dying. But that's the part that fascinates me. How does a car actually know its battery's dying? It's not a biological organism.
No, it doesn't have a nervous system to feel pain.
Right. It's just a sealed metal box full of chemicals.
And that lack of a biological nervous system is precisely why the software has to be so incredibly paranoid. The stakes here are astronomically high. In automotive engineering, specifically in design failure mode and effects analysis.
DFMEA.
Exactly, DFMEA. This specific fault is rated as a severity 8.
Wow. Severity 8.
Yeah, that is the highest possible danger level before you get into, instant fatality territory. If the car gets this math wrong or if it just ignores the physical decay inside that sealed box, we are talking about catastrophic thermal runaway.
Uncontrollable battery fires.
Exactly. So the software basically has to infer the health of the chemistry using nothing but electrical signals.
So today, we're going to explore the root causes of this physical degradation, the software architecture that is desperately trying to catch it, the manufacturing defenses built on the line to prevent it, and the rigorous torture testing these systems go through before you can even buy the car.
It's a massive journey.
It really is. So let's start with the physical reality, because before we can understand how the software protects the battery, we have to understand the microscopic war happening inside it. What is the fundamental root cause of this decay?
Well, the physical decay that eventually triggers that I067 code boils down to, like you said, an invisible war inside the cells. The source material breaks this down into a few distinct mechanisms, starting with microelectrochemical decay. And the first major culprit is known as LLI.
Loss of lithium inventory. The battery is completely sealed. The lithium can't be leaking out onto the pavement. So when you say lost, you mean it's just becoming permanently locked away inside the cell.
That captures the dynamic perfectly. It is locked away. Inside a standard lithium-ion battery, you have this liquid electrolyte sitting between the anode and the cathode.
Okay, the positive and negative sides.
Right. And over thousands of charging and discharging cycles, or, especially when the battery sits in high ambient heat for a long time, this liquid electrolyte chemically reacts with the graphite anode, the negative side.
Right, I'm with you.
And this reaction forms a very thin barrier layer called the solid electrolyte interface, or the SEI layer.
Now wait, from what I understand about battery chemistry, isn't a little bit of that SEI layer actually a good thing? Like it protects the anode from just infinitely reacting with the liquid, doesn't it?
Oh, it's entirely necessary. When a battery is first manufactured, engineers actually run it through a really slow, careful charge, specifically to build up that initial SEI layer.
Oh, wow. I didn't know that.
Yeah. But the long-term problem is mechanical. As the battery breathes, because it physically expands slightly when you charge it and contracts when you discharge it over years of use, that SEI layer experiences relentless stress.
Because it's expanding and contracting.
Exactly. And it's not perfectly elastic, so it cracks. And when that thin protective crust cracks, microscopic patches of fresh graphite are suddenly exposed to the liquid electrolyte again.
Which just causes another chemical reaction.
Immediately. The chemistry rushes in to repair the crack, which forms more SEI layer, but that repair process actually consumes active lithium ions to build the new material, so it thickens the layer.
Oh, I see.
And then the next time the battery expands, it cracks again, it repairs again, it thickens again, just over and over for the entire lifespan of the car.
Okay, let me see if I can visualize this. So if the battery's like a bustling city and the lithium ions are the commuters traveling back and forth between their homes at the anode and their jobs at the cathode.
Well, this analogy, yeah.
Okay, so LLI basically means these lithium commuters are getting permanently stuck in traffic jams, or actually literally paved over by constant road repair.
Paved right over.
Right. The SEI layer is like scar tissue.
Mm-hmm.
Just keeps getting thicker, trapping the commuters inside it. So eventually you just don't have enough active commuters left to carry a charge.
That is a very apt way to put it. The charge capacity collapses nonlinearly because you are literally running out of active, moving lithium. It's completely deadlocked in that thickened scar tissue.
Man. Okay, but is that the only problem?
No, actually, it's worse. Because while the commuters are getting trapped by road repairs, the city itself is also physically crumbling beneath them.
Oh, boy. And that brings us to the second acronym in the document, LAM. Loss of active material.
Yes. LAM is particularly prevalent in modern, really energy-dense, high-nickel cathodes. When you subject these advanced materials to high C rates combined with thermal fatigue, the actual physical crystalline structure of the cathode starts to fail.
Okay, let's define C rate for a second because that gets thrown around a lot in EV spaces. A high C rate means pushing or pulling a massive amount of current relative to the battery size.
Right. Exactly.
So we were talking about like mashing the accelerator to the floor to show off your 0 to 60 time or pulling up to one of those ultra-fast 350 kilowatt DC chargers.
Those are prime examples. A 1C rate means charging the entire battery in 1 hour. Fast chargers can push 3C or even 4C, so they're trying to cram a full charge in 15 or 20 minutes.
That sounds aggressive.
It is violently aggressive at the chemical level. Those events force massive amounts of electrical energy through the fragile chemical lattice incredibly quickly. Over time, this extreme stress causes the transition metals, like the nickel and manganese, to literally dissolve into the electrolyte.
Wait, dissolve?
Yeah. Phase changes occur at the microscopic level, and the physical lattice collapses on itself. You get these microscopic mechanical cracks growing deep inside the electrode particles, and eventually, whole chunks of the material physically disconnect from the conductive network.
So going back to the city analogy, the bridges are collapsing.
Yeah.
The roads and office buildings are literally dissolving.
Exactly.
So even if the lithium commuters weren't trapped by the SEI scar tissue on the other side of town, they'd have nowhere to go when they arrive at the cathode because the infrastructure is physically shattered.
Right, it's disconnected from the power grid. The physical spaces where the lithium ions are supposed to slot in, a process called intercalation, they are destroyed forever. This permanently shrinks the maximum physical capacity of the battery.
What engineers call CMAX.
Precisely. So you have LLI locking up the active lithium and LAM destroying the physical storage space. But, that's just the microscopic reality inside a single cell. And we don't drive on a single cell.
We drive on thousands of them.
Exactly. We have to zoom out to the macro level, the entire battery pack.
And this is where the source material introduces a concept it calls thermophysical damage, or the bucket effect, which I assume is based on the old wooden bucket analogy.
It's a foundational engineering principle. Basically, a wooden bucket made of vertical staves can only hold water up to the height of its shortest stave. In a high-voltage battery pack wired in series, your total usable capacity is entirely dictated by the absolute weakest, most degraded single cell in the entire pack.
But wait, modern manufacturing is incredibly precise, right? Aren't all the cells in a brand new EV manufactured to be completely identical? How does one cell become so much weaker than the thousands of others right next to it?
They do start out identical, but their living conditions inside the car are never perfectly uniform. I mean, think about the liquid cooling channels winding their way through that massive battery pack under the floorboard.
Okay.
Fluid dynamics are complex. What if there's a tiny microscopic dead zone in the coolant flow near the corner of the pack? Or what if the thermal interface material, the paste that transfers heat from the cell to the cold plate, has a microscopic air bubble trapped inside it?
Ah, from the exact moment it was dispensed at the factory.
Right.
And that air bubble acts as an insulator. So that specific cell can't cool down as effectively as its neighbors. It's basically wearing a winter coat while everyone else is in t-shirts.
That's exactly the issue. It creates a localized hotspot. And this is where the physics of aging become mathematically aggressive, governed by something called the Arrhenius equation.
The Arrhenius equation. Okay,
Yeah.
let's unpack that. I remember the name from, like, college chemistry, but remind me how it works for battery degradation.
Yeah. At its core, the Arrhenius equation describes how the rate of a chemical reaction changes with temperature. And the critical takeaway is that the relationship is exponential, not linear.
Exponential.
Yes. Chemical reactions, including the destructive LLI and Lamb reactions we just talked about, accelerate exponentially as heat increases. If the maximum temperature difference between cells in a pack exceeds just 3 to 5 degrees Celsius,
Hold on, 3 to 5 degrees Celsius, that is a tiny difference. If my living room is 70 degrees or 75 degrees, I barely even notice.
it feels tiny to a human, sure. But to the fragile electrochemistry inside a high-nickel battery cell, a persistent 5-degree temperature gradient is massive. Under the Arrhenius effect, the cell sitting in that slightly warmer hotspot with the air bubble under it is going to age exponentially faster than the rest of the pack.
Wow.
Its self-discharge rate spikes, its direct current internal resistance, or DCIR, violently diverges from the other cells.
So that one warm cell becomes the short stave in the wooden bucket. It degrades faster, its capacity shrinks faster, and because they're all wired together in a massive chain, it basically drags the entire multi-thousand-dollar battery pack down with it.
It forces all the healthy cells to stop working just because it's exhausted.
That is why.
It creates a huge bottleneck. But here is the crux of the entire document, that physical decay creates an absolute existential crisis for the software. And this is where the real danger lies.
It's a math problem.
Exactly. If the battery's physical health is decaying in the background, but the car's computer doesn't realize it, you have a recipe for total disaster.
The document calls this software parameter divergence.
Right. The car's non-volatile memory stores an incredibly important parameter called state of health, or SOH. If the battery management system, the BMS, fails to continuously and accurately measure the decay and update this SOH parameter, the software simply continues to do its math based on the beginning of life capacity.
A capacity the battery had on the literal day it rolled off the assembly line. Oh, I see. It's like balancing your checkbook, thinking you still have the massive salary from a job you had 10 years ago, completely ignoring the fact that you took a major pay cut. You are going to confidently write a check that is going to bounce violently.
And in this case, bouncing a check leaves you stranded on the highway. The dashboard is essentially lying to you. The system calculates your remaining range by dividing your current stored energy by a maximum capacity number that physically evaporated years ago due to LLI and Lamb.
So the dashboard cheerfully tells you that you have 100% charge. You think, great, I can confidently drive 300 miles into the desert.
Well,
but the physical reality is your true capacity is severely compromised.
and what happens when you try to accelerate hard to merge onto the highway or drive up a steep mountain pass relying on that phantom capacity?
You demand a massive amount of current from a cell that is internally shattered.
And the math and the physics violently diverge. The battery's voltage will suddenly and sharply collapse under the heavy load because the physical energy just isn't there, and the internal resistance of that degraded hotspot cell is way too high.
So what does the car do?
The car's low voltage systems might detect the voltage collapse and just shut the main contactors off entirely to protect the circuits, leaving you instantly without power at 70 miles an hour.
Terrifying.
Or infinitely worse, the extreme electrical stress pushing through those degraded, high-resistance cells could generate so much localized heat that it triggers a thermal event.
A fire. Okay, so that is terrifying. The physical decay is inevitable, right?
Right.
The LOI trapping the commuters, the LAM destroying the infrastructure, the hotspots accelerating the Arrhenius equation. It's going to happen eventually.
Law of physics.
Right. So since physical decay is essentially guaranteed over a long enough timeline, how does the battery management system catch the falling knife before the battery catches fire? How does it actually figure out the true health of the battery so it stops lying to the driver?
This brings us to the technical architecture and fail-safe mechanisms, the brains of the operation. To solve this mathematically complex problem of invisible decay, the BMS uses something called a dual timescale observer.
Dual timescale observer. I mean, that sounds like a device from a Christopher Nolan movie. What are the two timescales we're talking about here?
The engineers essentially decoupled the math into two separate streams of time. You have the fast variable, which is the state of charge, or SOC.
Okay.
That is just answering the question, how much fuel is in the tank right this second? That has to be calculated in real time, hundreds of times a second, so the dashboard gauge is accurate while you drive.
Makes sense.
But then you have the slow variable, the state of health, the SOH. That is answering the question, how big is the tank itself? That's calculated on a much slower, longer timescale, maybe only updating every few full charging cycles or like once every 24 hours.
Wait, why have the separation? Why not just calculate both of them all the time? If my battery is degrading, wouldn't I want the computer to know its exact health every single second I'm driving?
You would certainly want to, but the laws of electrochemistry basically prevent you from doing the math accurately while the car is in motion.
Really?
Yeah. When you are driving, you're demanding massive, constantly fluctuating transient currents from the battery. You accelerate, you brake, you accelerate again. These massive swings in current create something called polarization, voltage drops.
Polarization, meaning the voltage gets, like, distorted.
Essentially, yes. When a massive current moves through the battery, ions build up near the electrodes faster than they can be absorbed, creating a temporary internal resistance. This temporarily warps the voltage readings. It's like trying to accurately measure the exact depth of a swimming pool while someone is repeatedly doing cannonballs into it.
Wow.
The water is violently sloshing everywhere. The level on the side of the pool is constantly jumping up and down.
Okay, that makes perfect sense.
Yeah.
The waves from the driving current make it impossible to see the true calm water level.
Exactly. So the BMS has to patiently wait for quiet moments. It needs the car to sit perfectly still, usually when parked and asleep, so it can take a true open circuit voltage or OCV reading.
It waits for the pool to settle.
Right. It waits hours for the polarization effects to naturally dissipate, for the waves in the pool to stop sloshing. And then, once it's calm, it quietly does its amp hour integration. It looks at exactly how much energy went in, how much came out, and uses highly complex algorithms like adaptive Kalman filtering to deduce the true capacity.
Let's pause on adaptive Kalman filtering. That is a heavy technical term. How does a Kalman filter actually work in this context?
So a Kalman filter is a recursive mathematical algorithm that's very famous in aerospace and navigation. It takes a series of measurements observed over time, which are inherently full of noise and inaccuracies, and produces an estimate of unknown variables that tends to be much more accurate than a single measurement alone.
Okay, so it's constantly guessing, checking its guess against reality, and then updating its internal model.
Yeah, that's a good way to look at it.
Like maybe driving through a long tunnel where you lose your GPS signal. The car's navigation system has to guess your location based on your last known speed and direction. It knows it's accumulating a little bit of error every single second. But the moment you exit the tunnel and get a satellite signal again, it instantly corrects its location, figures out how wrong its guess was, and updates its internal math so its next guess is better.
That is a phenomenal analogy for a Kalman filter. Yes. The BMS is driving through the tunnel of noise while you are accelerating and braking. It is just guessing the health.
Right.
But when the car finally goes to sleep and the voltage settles, the BMS gets its GPS signal back. It takes an accurate OCV reading, compares it to what it predicted the reading would be, calculates the error, and permanently updates the state of health parameter in the long-term memory.
Okay, that makes total sense. If I completely drain my battery to 0 and then completely charge it up to 100% overnight, the car gets a massive clean look at the entire capacity of the battery.
Right.
But here is the obvious problem with that. What about drivers who never ever do that? What about someone who just drives 3 miles to the grocery store, plugs in for an hour on a slow charger, drives home, plugs in again? They only ever fluctuate between, say, 50% and 70% charge.
Shallow chargers.
Yeah. They never empty the pool, and they never fill the pool. So how does the Kalman filter measure the depth of the pool if it only ever sees the middle 20%?
That behavioral reality is actually one of the most brilliant parts of the software layer we are looking at. For the shallow chargers, the BMS cannot rely on full amp-hour integration. Instead, it deploys a technique called incremental capacity analysis, or ICA.
Incremental capacity analysis. I'm assuming this involves some serious math based on the outline calling it dQ/dV.
It is entirely calculus-based. dQ over dV. Q stands for electrical charge, and V stands for voltage.
You are giving me high school AP calculus flashbacks right now. The rate of change of charge relative to the rate of change of voltage.
That's it. The BMS is continuously running high-frequency calculus in the background. Even if you are just doing a slow, boring AC charge in your garage from 40% to 60%, the software is meticulously monitoring the tiny microscopic changes in electrical charge going in relative to the tiny microscopic changes in the battery's voltage response.
Wow.
As the lithium ions interleave into the graphite, as they find their parking spots, the chemical reactions inside the cell create very specific electrochemical peaks or signatures in the data. If you plot dQ/dV on a graph, it looks like a series of bell curves.
Okay, so it's like looking for specific landmarks on a map?
Yeah.
Even if I'm only driving a short 2-mile segment of a highway, if I see, like, the big water tower and the specific oddly shaped bridge, I know exactly where I am on the larger map, even without seeing the whole road.
The BMS is doing exactly that with electrochemistry. And here's the genius part. As the battery ages, as LLI and LAM destroy the cell, the height, the width, and the position of those bell curve peaks physically shift on the graph. They move to a higher voltage, or they shrink in amplitude. So by running this calculus, the BMS can identify those shifting peaks in just a small 20% charging window, compare them to the factory baseline, and mathematically deduce the true full capacity of the entire battery, without ever actually needing you to do a full 0 to 100% cycle.
That is just incredible. It's mathematically inferring the total health of the entire system from just a tiny slice of behavioral data.
It really is elegant.
Okay, so the BMS is constantly watching, doing calculus in the background, updating the slow-moving state of health parameter via the Kalman filter. But what happens when that math finally comes back with a terrifying answer? What happens when the BMS realizes, oh no, the health has dropped to a critical level, the physical decay has gone too far?
That is when the hammer drops. That is the exact moment the BMS Theory 6.7 fault is triggered.
The doomsday code.
When the system is absolutely mathematically certain, usually after confirming the calculation across multiple driving and charging cycles so it knows it isn't just a temporary sensor glitch, that the total capacity has dropped below the critical safety threshold, which is typically around 70% to 75% of its original factory capacity. It takes drastic, irreversible action.
It deploys the safety fortress we talked about at the beginning.
Exactly. The level 2 safety logic instantly writes a permanent fault flag directly into the non-volatile memory, or NVM. And non-volatile means this data survives even if the car loses all 12-volt and high-voltage power.
It's burned in.
Yes. This is not a simple check engine light that you can just clear with a cheap OBD2 scanner you bought online. It is locked into the silicon forever. And the behavioral punishments the car inflicts on itself are severe.
Let's talk about those punishments. What does the car physically stop you from doing once that flag is set?
First, pure EV mode is disabled entirely. If you are in a plug-in hybrid, the engine turns on and stays on. If you're in a pure EV, the maximum power output is just slashed. DC fast charging, permanently banned. The car will digitally refuse to shake hands with a fast charger.
Because pushing high current into a severely degraded battery is a massive thermal runaway risk, right? If the lithium commuters are already trapped by the SEI layer and you force hundreds of amps into the cell too fast,
they cannot interleave into the graphite. They back up. They literally plate onto the surface of the anode as solid metallic lithium, creating dendrites that can pierce the separator and short-circuit the cell, causing a fire.
So fast charging is locked out. For your own safety.
Furthermore, your maximum charge limit is hard capped by the software. The car will physically not allow you to charge past 50% or maybe 80% at the absolute maximum, no matter how long you leave it plugged in.
It intentionally keeps the battery away from the high voltage extreme to prevent overstressing those fragile, decayed cells.
Exactly. And this is what triggers the limp-home mode that ruins your day on the highway. While driving, the car violently slashes the maximum motor current and speed. The depth of discharge, or DOD window, is aggressively narrowed.
So instead of letting you use the full spectrum of the battery, it might only let you use the middle chunk, say from 30% to 70%.
Right. It is doing everything in its mathematical power to keep the battery in a safe, stress-free middle ground so you can safely pull over or limp to a service center without the vehicle catching fire.
It is basically treating the battery like an incredibly fragile ticking time bomb, which honestly, at 70% health with high internal resistance, it essentially is.
It is.
But wait, doesn't the manufacturer want to know about this before it happens? I mean, if I'm stranded on a highway in limp-home mode having a heart attack because my car just lost 70% of its power, I'm going to be a very angry customer. I'm calling a tow truck and I'm yelling at the dealership.
The manufacturer desperately wants to avoid that entirely for both safety and, frankly, warranty cost reasons. And that brings us to the broader architecture. The cloud digital twin.
The eye in the sky.
Exactly. Modern connected EVs are constantly sending high-frequency telemetry back to the manufacturer's cloud servers. We are talking charging behavior, ambient temperature data, voltage curves during acceleration, internal resistance estimates.
Everything.
The cloud maintains a massive digital twin, a virtual simulation of your specific physical battery pack, and it compares your daily data to the aggregate fleet data of hundreds of thousands of other cars on the road.
So it's looking for statistical patterns. It sees that, okay, thousands of cars with a similar climate profile and fast charging habit to mine tend to hit that 70% death knell right around the 5 years, 60,000 mile mark.
Precisely the concept. And because the cloud has vastly more computing power than the small BMS processor inside the car itself, it can spot the degradation trend much earlier. Before your battery even hits that 70% failure threshold, say, when the Kalman filter reports it is at 75%, the cloud can preemptively intervene. It pushes a silent over-the-air, or OTA, update specifically targeted to your car's VIN.
A targeted digital intervention. What does the update actually tell the car to do?
It downloads a deer rating map. It quietly overrides the factory settings and tells your car's BMS, hey, this specific battery pack is aging poorly, the internal resistance is climbing. Let's proactively slow down the maximum DC fast charging speeds by 15%, and let's lower the maximum torque output of the motors just a tiny bit.
Wow. And the driver might barely notice it, right? Maybe their fast charge takes 32 minutes instead of 28 minutes.
Right, but this preemptive DERA rating significantly reduces the daily mechanical and thermal stress on the battery. It flattens the degradation curve, delaying that ultimate Air 067 failure and giving the owner time to get a routine service check gracefully rather than breaking down on the highway.
That is just phenomenal engineering. The car is basically tattling on its own failing health to the cloud, and the cloud is sending back a bespoke digital prescription to keep it alive a little longer.
It's a beautiful system.
Okay, so that is how the software architecture frantically catches the failure in real time. But let's rewind the clock to the very beginning. It is one thing to have a fantastic alarm system when the battery is failing, but as an engineer, you don't want to rely solely on the airbag. You want to avoid the crash entirely.
Obviously.
How do they mathematically and physically build these batteries so that this decay is delayed as long as humanly possible from day one?
This brings us to the design phase, specifically DFMEA, Design Failure Mode and Effects Analysis. This is where we look at how the physical fortress is actually drawn up on the blueprints.
Okay.
As we noted, hitting a capacity limit is a severity 8. It's the top tier of danger. So the engineers have to design physical and mathematical buffers into the system before it ever leaves the CAD software. One of the most critical physical design parameters mandated in the document is the NP ratio.
NP ratio, negative to positive ratio.
Correct. It represents the ratio of the physical active material coated on the negative anode compared to the active material coated on the positive cathode. In these high-voltage systems, engineers mandate an NP ratio of greater than or equal to 1.1.
Wait, hold on. Let me look at this. They aren't just making the two sides equal. They're intentionally overbuilding the negative anode by exactly 12% or more. Why the asymmetry? Why waste the money and the physical space inside the cell, putting 12% extra material on just one side?
It is entirely about creating an extreme safety margin, specifically during DC fast charging and freezing cold temperatures. Remember our lithium commuters trying to get home.
Yep, the lithium ions trying to interleave into the graphite anode during a charging session.
Right. When the battery is physically cold, say, parked outside in winter, the electrochemistry becomes incredibly sluggish, the commuters are moving in slow motion, the liquid electrolyte is viscous.
Okay, that makes sense.
If you plug into a massive fast charger and hit the battery with a huge surge of power when it is freezing cold, those lithium ions are forced over to the graphite anode at high speed, but they cannot physically slot into the crystalline lattice fast enough because the reaction kinetics are slowed down by the cold.
So they arrive at the parking lot, but the gates are opening too slowly.
And if there isn't enough raw physical surface area for them to spread out while they wait, they start to pile up on the surface of the anode. Instead of safely interleaving, they undergo a phase change and turn into solid metallic lithium. This is the lithium plating we mentioned earlier, the formation of dendrites.
And dendrites are those tiny, microscopic metallic spikes that grow like stalagmites. And they can eventually grow tall enough to puncture the thin plastic separator between the anode and cathode, shorting out the battery from the inside.
They are the ultimate enemy of battery safety. So by intentionally overbuilding the anode by 12%, the engineers are essentially building a massive, extra-large overflow parking lot for the commuters. It mathematically guarantees that even if the lithium ions arrive too fast, and even if they are sluggish from the cold, there is vastly more than enough physical surface area for them to safely spread out, completely cutting off the localized current density required for those deadly dendrites to form.
Okay, that makes sense for preventing an instant short circuit. But wait, let me push back on this for a second.
Yeah.
We established earlier that the SEI layer, the scar tissue that traps lithium and causes LLI, grows on the surface of the anode.
Yes, it does.
If you intentionally add 12% more anode material, aren't you just creating a massive, extra-large surface area for the SEI layer to grow on? Aren't you basically giving it more real estate to pave over, meaning you will lose active lithium to LLI even faster over the life of the car? How is that a good trade-off?
That is the fundamental paradox battery engineers wrestle with daily, and your deduction is spot on. You are completely correct that adding more surface area marginally accelerates early life loss of lithium inventory. It does eat a small percentage of your capacity over time.
So why do it?
Because it is an intentional, calculated sacrifice. Engineers will gladly sacrifice a small amount of long-term range to LLI if it means guaranteeing the battery will never form a dendrite and instantly catch fire during a cold fast charge. Safety preventing a severity 8 event always trumps total capacity.
Wow. It is a purely physical design sacrifice to prevent a chemical disaster.
Yay.
Okay, what else do they design into the software to delay the decay? The outline mentions an algorithm called cumulative damage and rainflow counting.
Yeah, rainflow counting is a fascinating algorithm. It was originally developed in the 1960s for metallurgy and aerospace engineering. They used it to track the cumulative mechanical fatigue on an airplane wing as it experienced varying wind gusts. Battery software engineers adopted the exact same math to track the invisible fatigue inside the battery cells.
So it's not actually about rain or water at all. It's about counting stress cycles.
Right. It looks at the hysteresis loops of stress. A battery doesn't just age based on how many simple times you plug it in. It ages based on a complex web of factors. The specific depth of the discharge, the ambient temperature during the drive, how violently you accelerated on that specific day.
It's all cumulative.
Exactly. The BMS software continuously runs this rainflow counting algorithm to dynamically tally up all the microstresses. It calculates the total cumulative life cycle, stress thermal, electrical, mechanical, in real time.
And what does the car actually do with that running tally of stress?
It uses it to dynamically adjust the safe operating windows. If the rainflow algorithm sees that the battery has had a particularly hard life, say the car lived in Arizona, experienced lots of hot weather, and was constantly fast-charged by a heavy-footed driver, it will autonomously lower the maximum charging currents and power limits earlier in its life than a car driven gently in a mild climate.
Wow.
It bespoke tailors the protection to the actual abuse the battery has suffered.
Which feeds perfectly into the concept of graceful degradation. The car isn't just going to wait until the battery is at 70% health and then suddenly freak out, throw the A067 code, and shut down on the highway without warning.
The entire system is architected with multiple escalating warning tiers. At 80% state of health, it might silently restrict some top-end motor power without telling you. At 75%, it will likely give you a mild dashboard warning, battery degradation detected, schedule service, and further reduce the state of power.
So by the time you actually hit that catastrophic 70% mark, the system has progressively and smoothly turned down the performance over months or years, so the driver is never caught completely off guard by a sudden, violent loss of power.
It's basically letting you down easy.
Okay, so the design is incredibly robust. The rain flow math is brilliant. The physical 12% overbuilding of the anode is a genius compromise. But, and this is a massive, a perfect design running in a computer simulation means absolutely nothing if the factory builds the physical object wrong.
Oh, 100%.
Which shifts our focus to the manufacturing side. How do manufacturers defend the assembly line? How do they ensure the physical metal and chemical battery actually matches the pristine mathematical model in the software?
This is where things get intensely strict, moving into PFMEA, process failure mode and effects analysis. On the factory floor, they have to rigidly control what are called key control characteristics, or KCCs. And one of the most sci-fi sounding methods they deploy is beta ray coding inspection.
Beta rays, that sounds intense. I mean, usually factories use high-speed optical cameras or lasers to inspect parts. Is there something about the active material that light just can't handle?
Optical cameras can only see the surface. They can tell you if the coating is there, but they can't tell you how dense it is inside. When they're manufacturing the electrodes, rolling out massive, mile-long sheets of copper and aluminum foil coated with the anode and cathode slurries, the precision required is sub-millimeter. So they pass 100% of that coated material through a scanner that blasts it with beta rays. Because beta radiation is absorbed and scattered based on the mass of the material it passes through, the sensors on the other side can measure the exact microscopic density and thickness of the active material coating in real time as it flies down the line.
And why is that density so critical?
Remember that 1.12 NP ratio we just discussed? The 12% overbuild anode parking lot to prevent the dendrites.
Right.
Well, if the coating machine hiccups for a fraction of a second and puts a microscopic thin patch of anode material on the edge of the foil, suddenly, in that one tiny millimeter spot, your local NP ratio might drop below 1.0.
Oh, and that one tiny thin spot doesn't have enough parking spaces. It becomes a localized focal point for lithium plating, a weak point in the armor that will grow a dendrite and kill the cell, even if the rest of the battery is perfectly built to 1.12.
A single microscopic thin spot ruins the entire cell. The beta ray inspection ensures there is absolute, unyielding uniformity in the coating density, preventing those localized imbalances. Another critical KCC is the electrolyte volume and sealing pressure.
How do they control that?
They use strict statistical process control, or SPC, to monitor the exact micrograms of liquid electrolyte injected into each individual cell and the exact physical force used to laser weld the cell shut.
Because if a cell has a microleak at the weld, the liquid electrolyte slowly evaporates over the car's lifetime. The commuters literally lose the liquid they swim in.
And when they do, the internal resistance skyrockets and the capacity collapses locally, eventually triggering our doomsday code, A067, just from a bad weld.
Amazing.
But perhaps the most critical step on the entire assembly line regarding the software architecture is what the document calls the MES database binding, the birth certificate of the battery.
Okay, let me make sure I understand this. You were saying that if a physical battery cell isn't introduced to the software properly on the day it is born, the whole Kalman filter mathematical model we talked about falls apart years later.
Without a doubt. You have to remember the BMS algorithms, the Kalman filters, the rain flow counting, the ICA calculus, they all rely fundamentally on knowing their starting point. They need a baseline to calculate decay.
Okay.
When a battery module is assembled, every single cell is physically tested on the line. Its exact initial amp-hour capacity, its exact AC internal resistance, and its unique serial barcode are scanned into the factory's overarching computer system, the manufacturing execution system, or MS.
And then what happens to that data? Does it just live on a server somewhere?
No, at the end of the line, that specific unique data set is permanently burned into the BMS EEPROM memory of the specific car that module goes into. It is the baseline.
What if something goes wrong?
Well, if there is a networking glitch on the factory floor and those memory registers were accidentally left blank, say they initialized with null values, or the hexadecimal code 0xFF, which basically means empty to a computer, the algorithms would have absolutely no baseline.
The computer would wake up with amnesia.
Exactly the problem. The moment you drove the brand new car off the lot, The state of charge and state of health calculations would immediately jump wildly as the Kalman filter tried to guess a baseline from scratch.
Oh, man.
You'd have immediate, furious customer complaints about the range dropping from 100% to 0 in 5 minutes, all because of a missing text file on the factory floor.
The map simply explodes without the birth certificate.
It does. And the final ultimate step before the battery is allowed to leave the factory is the end of line, or EOL testing. They dynamically monitor the physical clamping force on the module so the cells aren't physically crushed by the steel casing. And 100% of the battery packs undergo a massive DCIR, direct current internal resistance test.
The outline explicitly mentions a strict process capability index required here, a CPK of greater than or equal to 1.67.
Yes, CPK.
Let's slow down on CPK, process capability index. What does a CPK of 1.67 actually translate to in plain English?
CPK is a statistical measurement of how tightly grouped a manufacturing process is relative to its allowable specification limits. A CPK of 1.0 means your process just barely fits inside the acceptable limits. A CPK of 1.67 essentially translates to 6 sigma quality.
Which is very high.
To put that into perspective, if you manufactured 1 million individual battery cells, a CPK of 1.67 dictates that statistically, only about one single cell out of a million would fall outside the acceptable internal resistance limits.
1 in a million. That is an absurd level of precision.
That is the level of absolute obsession required here, because just one bad cell with high resistance creates that bucket effect hotspot we talked about earlier, dragging the whole pack down. Only statistical perfection is allowed to leave the factory floor.
Okay, so let's take stock. We have a mathematically flawless DFMEA design. We have a 6 sigma PFMEA manufacturing process, shooting beta rays at the foil and burning birth certificates into the memory. We have the software baseline established.
Right.
Now, as an automaker, how do you absolutely 100% guarantee that this safety logic, this massive invisible fortress we've built, actually works in the real world, out on the highway, before putting it in a customer's driveway?
You torture test the system until it breaks. This brings us to the final discipline, DVP&R, or Design Verification Plan and Report. This is mass production validation. The engineers have to prove on physical test benches and in simulators, beyond a shadow of a doubt, that the A067 safety logic will fire correctly, accurately, and safely under the worst possible conditions imaginable.
Let's talk about these torture tests because they sound brutal. The first one listed is the ICA temperature torture test.
Remember ICA, the incremental capacity analysis, the DQ/DV calculus that infers the battery health just from shallow 20% chargers.
And high school calculus looking for the shifting bell curves of electrochemistry.
Yeah. Well, it is relatively easy for a software algorithm to find those electrochemical peaks in a pristine, brand new battery sitting in a climate-controlled 70-degree laboratory. But what about a battery that has been through hell?
Okay, what do they do to it?
The engineers take a heavily aged physical battery, say one they have manually run through 800 deep charging cycles, so it is hovering right around 72% health, dangerously, terrifyingly close to the failure limit. They put it in a massive environmental testing chamber.
Oh, they freeze it.
They drop the ambient temperature to negative 10 degrees Celsius. Then they test it again at a perfect 25 degrees. Then they bake it at 40 degrees. And at each temperature extreme, they run partial, messy, shallow AC charges. They actively try to confuse the software by not giving it a clean, full charge cycle.
They're essentially trying to make the calculus fail by throwing noise and temperature extremes at it.
And the criteria for passing this test is unforgiving. The software's calculated guess of the battery's true health must be within a rigid plus or minus 3.0% of the actual chemical laboratory measurement of that cell. If the software gets confused by the freezing cold or the extreme age of the cell and guesses wrong by 4%, the entire software validation fails.
Plus or minus 3% accuracy on a nearly dead, freezing cold battery using only partial, shallow charging data. That requires an insane level of mathematical precision.
It has to be that precise, or the car will leave someone stranded. But that is just the math test. The next test is a hardware-in-the-loop test that feels straight out of an action movie. The 12V brownout AHL test, the microsecond save.
This test raises an important question for me about how the electrical systems actually interact. Let's say the high-voltage battery is dying. It hits 68% health. The BMS does the math, realizes this, and prepares to write that permanent fault flag, the Doomsday A067 code, into the non-volatile memory.
Right.
What happens if the car's regular 12-volt accessory battery dies at the exact microsecond the computer is trying to save the file? Why would the 12-volt die in the first place?
A very insightful question. The high-voltage battery feeds the 12-volt battery through a DC-DC converter. When a high-voltage battery suffers a severe internal fault and the main contactors forcibly open to prevent a fire, the 12-volt system suddenly has to take the full electrical load of the entire car.
Like the computers, the power steering, the brakes.
Exactly. And the 12-volt system can experience a massive sudden voltage sag, a brownout.
So the computer's trying to write its last will and testament while the power grid of the car is actively collapsing around it.
That is exactly what this test simulates. What if the power cuts out midway through writing the word danger to the hard drive? If the file gets corrupted mid-write, the next time you turn the car on, it might read the file as corrupted or blank. The BMS might wake up and think the battery is perfectly fine.
And it blindly allows you to go plug into a 350 kilowatt fast charger with a critically degraded battery, which leads to instant lithium plating, thermal runaway, and a fire.
The stakes couldn't be higher. So, on the hardware in the loop test bench, the engineers inject the halt code. The BMS processor starts writing to the permanent EEPROM memory. And right in the middle of that microsecond write operation, the engineers artificially drop the 12-volt power supply down to 4.5 volts.
They simulate a massive grid collapse.
Yes.
How does the computer possibly survive that to finish the job?
The physical circuit board of the BMS is designed with a hardware backup, a dedicated, isolated capacitor. This tiny electronic component must hold just enough electrical juice in reserve to keep the processor and the memory chip alive for greater than or equal to exactly 50 milliseconds after the main power dies.
50 milliseconds. That is a fraction of a blink of an eye.
It is just enough time for the processor to finish writing the fault code block, execute a checksum CRC, and safely shut down.
Explain the checksum CRC. How does the computer know it didn't just write gibberish?
A CRC, or cyclic redundancy check, works a lot like the receipt you get at the grocery store. The system counts up all the data bits it just wrote to the memory, generates a mathematical receipt based on that data, and saves it. When it reads the file later, it recalculates the receipt.
Okay.
If the new math doesn't perfectly match the saved receipt, it knows the file was corrupted during the brownout.
And what happens if the receipt doesn't match? Is the car just bricked?
This is where the redundancy comes in. The system must prove it can self-repair using an AB software partition. It essentially has dual isolated backup drives. If it realizes partition A was corrupted by the power loss, it seamlessly flips to partition B to try saving again or to read the last known good state.
Incredible.
If the capacitor fails to hold power for 50 milliseconds or the CRC check fails to catch corruption, the entire board design is rejected.
Okay, so the computer survives the simulated power failure. It wrote the code. But what about the physical moving car? What if you were doing 75 miles an hour on the highway when the BMS decides the battery is critically dead and triggers the code?
That brings us to the limp-home 2-second rule test. When ESR67 is triggered in a simulator running at highway speeds, the system has a fault-tolerant time interval, or FTTI, of exactly 2.0 seconds to react.
2 seconds to do what exactly?
To completely reconstruct the vehicle's power dynamics. In 2.0 seconds, it must communicate with the main vehicle control unit, turn on the severe warning lights, and aggressively cut the motor power down to 30% or 50%. But, and this is a massive engineering challenge, it has to do it smoothly.
Right, because if you just instantly sever 70% of the power to the drive wheels while someone is maneuvering on the highway, the physical jolt, the sudden torque jerk, could cause the driver to lose control, spin out, and crash.
Precisely. So within that strict 2.0 second window, the software has to smoothly logarithmically ramp down the torque so it feels like a heavy deceleration rather than a physical impact. It locks out pure EV mode, permanently bans fast charging by communicating with the charge port controller, and alters the thermal management parameters.
It turns your high-performance EV into a wounded, heavily restricted machine.
Yes, but it executes the transition safely and predictably without unsettling the chassis.
And finally, the final exam for the whole system, the Cloud OTA preemptive strike, testing the eye in the sky we talked about.
To validate the cloud AI, they run massive digital simulations connecting the physical test benches to the actual manufacturer cloud servers. They feed the cloud a stream of telemetry data from a simulated battery that is rapidly approaching the 70% death limit, simulating years of abuse in a few days.
So they feed it bad data.
Right. And the cloud architecture must prove it can spot the degradation trend before the physical breakdown occurs, automatically generate the specific OTA derating map, push it to the car over the cellular network, effectively cut the fast charge currents by 15% to 30%, and alert the simulated driver's phone app to schedule service.
What is the passing grade for this cloud simulation?
100%. The validation requirement is that 100% of unexpected physical breakdowns resulting from this specific failure mode must be blocked by the cloud predictive AI. Zero false negatives are allowed in the validation run.
Let's just take a breath and summarize the sheer scale of the engineering journey we have unpacked today. We started at the absolute microscopic level, looking at the invisible war of LLI and LAM. We saw lithium commuters getting physically trapped in the thickening scar tissue of the SEI layer.
Yeah.
We saw the physical, crystalline bridges of the high-nickel cathode dissolving and crumbling under the stress of heat and ultra-fast charging.
And then we moved up to the macro system level, seeing how a tiny, localized 3-degree temperature difference from a trap air bubble can trigger the Arrhenius equation, creating exponential hotspots that drag the whole multi-thousand-dollar battery pack down like the shortest stave on a wooden barrel.
And when that physical decay inevitably happens, we explored the mathematical genius of the software architecture, desperately trying to measure it. The BMS doing high school calculus, that DQ/dV incremental capacity analysis, to figure out the true health of the battery, even if you only ever charge it a little bit at a time.
The dual timescale decoupling the fast, chaotic waves of the driving current from the slow, deep truth of the battery's capacity using adaptive Kalman filters.
We unpack the unyielding rigidity of the failsafes, the permanent non-volatile memory fault flag, the immediate physical ban on fast charging to prevent dendrites, the forced limp-home mode that smoothly and predictably cuts your power in under 2.0 seconds to keep you from causing a thermal event at highway speeds.
And we looked at the design compromises, how engineers willingly sacrifice a little bit of capacity to overbuild the anode by 12% just to give the sluggish, freezing cold lithium ions a massive parking lot so they don't form deadly dendrites.
We saw factories shooting sub-millimeter beta rays at the assembly line to guarantee coding density and burning permanent birth certificates into the memory so the math always has a baseline.
And finally, the grueling, brutal validation process. Freezing dying batteries to test their calculus, intentionally cutting the main power to test a 50-millisecond backup capacitor and a grocery receipt checksum CRC, and forcing the cloud AI to prove it can predict the future with 100% accuracy.
It is truly breathtaking when you step back and realize how much invisible labor and mathematical obsession is happening right beneath your feet while you just listen to the radio. So the next time you are driving your EV in the dead of winter and you notice that it's dynamically adjusting your estimated range, or maybe you pull up to a DC fast charger and it's charging just a little bit slower than you'd like, don't be annoyed.
Yeah, don't be.
You are witnessing an absolute masterclass in software, chemistry, and hardware working together in perfect, real-time harmony. It is a symphony of engineering designed to protect you from the unforgiving physics of aging.
It is an invisible fortress, and its only purpose is keeping you safe.
Before we sign off, I want to leave you with one final fascinating thought pulled straight from the margins of this engineering document. We talked about that tiny, isolated backup capacitor, the one that has to keep the computer alive for exactly 50 milliseconds during a massive power brownout, just so it can write the final warning code to memory.
Right, the 50-millisecond save.
Because saving that fault flag is so fundamentally critical to preventing a battery fire. Imagine the complex Python simulations engineers have to run right now in laboratories around the world just to perfectly size that one tiny, cheap electrical component.
Oh, the modeling must be insane.
They are simulating microscopic voltage drop profiles, mapping out exact microsecond timelines, running thermal degradation models on the capacitor itself, all to ensure it is neither too big to waste space nor too small to fail its critical mission. It just goes to show you that in the world of high-voltage electric vehicle safety, the difference between a safe, controlled shutdown on the side of the highway and a total catastrophic disaster often comes down to just a few fractions of a second and a few lines of incredibly paranoid code. Thanks for diving deep with us.